When we first talked about induction, we were talking about using the natural numbers to index the elements of our set. Well, we don't have to necessarily use the natural numbers. We can use any subset of the integers. And the key with the natural numbers was that 1 was the smallest element in that set of positive integers. So as long as our set has a smallest element, we can build from there. So we always used 1 as our starting point when we first talked about induction, but there's really nothing stopping us from using some other integer as a starting point and building from there. So that's going to be what we talk about today with a more general principle of mathematical induction. So we can have a set of integers. They can be positive and negative as long as there's some element that is the smallest element in the set, and the set consists of all the integers greater than that element. So we're going to call the smallest element m. Now, that set of integers that are greater than or equal to m is a well-ordered set. Since it's well-ordered, we're set up to be able to use the principle of mathematical induction. So if we have a fixed integer m, that's going to be the smallest integer in our set, and we have a set of all of the integers greater than or equal to m, then for each integer in the set, we're going to have p of n being some statement. Then if we can show that p of m is true, so the statement is true for the smallest integer in the set, and we can show the implication if p of k, then p of k plus 1 is true for every integer k in the set, then p of n is true for every n in the set. So there's really nothing different about this except for our base case. Our starting point is going to be m instead of 1. The implication that we're proving is still the same. The only thing that we have in addition to this is we know k is greater than or equal to m instead of k being greater than or equal to 1. That's the only difference. So this is a more general principle, and it's really changed just a tiny bit. So don't stress out about this, all right? So let's take a look at an example. For every non-negative integer n, we want to show that 2 to the n is greater than n. Now notice we're dealing with non-negative integers here, so we're dealing with 0 up to infinity instead of 1 up to infinity like we were dealing with before when we were dealing with the positive integers. So to proceed by induction with our proof, we need to show the base case, that is, the minimum number in the set holds. So non-negative integers, the minimum value is going to be 0. So we'll show our base case for n equals 0. 2 to the 0 is 1, which is greater than 0. So our base case is true. Then we're going to move on using our inductive hypothesis. We're going to assume that 2 to the k is greater than k. K is going to be a non-negative integer. Now we need to show that 2 to the k plus 1 is greater than k plus 1. Now we're going to look at two cases here. The first one is when k is 0. K is the minimum non-negative integer. So we have 2 to the 0 plus 1, which equals 2. And that's greater than 1. And 1 was just 0 plus 1. So we have 2 to the k plus 1 is greater than k plus 1. Now let's take a look at the case where k is greater than or equal to 1. So if we take a look at one side of the inequality of what we want to show, so we'll look at the 2 to the k plus 1 side. Now we notice that 2 to the k plus 1 is really 2 to the k times 2. But 2 to the k is greater than k by our induction hypothesis. So that means that 2 times 2 to the k is greater than 2 times k. Well, 2 times k equals k plus k. And since k is greater than or equal to 1, we know that k plus k is greater than or equal to k plus 1. And that shows that 2 to the k plus 1 is greater than k plus 1. So, by the principle of mathematical induction, we have that 2 to the n is greater than n for every non-negative integer n, since we've shown the base case and the induction step. So let's take a look at another example. This time we're going to look at every integer n greater than or equal to 5. So 5 will be the smallest number in our set. And we're going to show that 2 to the n is greater than n squared. So we're going to do a proof by induction. The first thing we need to do is show the base case. Since 5 is the smallest element in the set, our base case is when n equals 5. So we'll show 2 to the 5 is greater than 5 squared. Now, if we just multiply 2 times itself 5 times, we'll see that it is in fact greater than 25. So the inequality holds when n equals 5. So now we need to use our induction hypothesis that 2 to the k is greater than k squared whenever k is greater than or equal to 5. And we're going to show that 2 to the k plus 1 is greater than k plus 1 squared. So again, we look at one side of the inequality. So we have 2 to the k plus 1, and that's going to equal 2 times 2 to the k. Well, by our induction hypothesis, we know that 2 to the k is greater than k squared, so 2 times 2 to the k is going to be greater than 2 times k squared. 2 times k squared equals k squared plus k squared. Since k is greater than or equal to 5, we know that k squared is greater than or equal to 5k. So we have k squared plus k squared is greater than or equal to k squared plus 5k. And we can break 5k into 2k plus 3k. So k squared plus 5k really equals k squared plus 2k plus 3k. Now we know that k is greater than or equal to 5, so 3k is greater than or equal to 15. So we know that k squared plus 2k plus 3k is greater than or equal to k squared plus 2k plus 15. Well, if we look at this, we know 15 is greater than 1, so k squared plus 2k plus 1 is definitely less than k squared plus 2k plus 15. And k squared plus 2k plus 1 equals k plus 1, the quantity squared. And through this series of equalities and inequalities, I find that 2 to the k plus 1 is greater than k plus 1, the quantity squared. So by the principle of mathematical induction, I have that 2 to the n is greater than n squared for every integer n greater than or equal to 5. So there's another example here using divides. So I'm going to leave this one for you guys to take a look at on your own. And it keeps on going on the proof. I'm also going to leave this theorem and its proof for you to look at on your own as well. And the proof continues onto a second slide. So in talking about that general principle of mathematical induction, we talked about how the base case doesn't necessarily have to be 1. Well, I also want to talk about this idea of the strong principle of mathematical induction. And in the strong principle of mathematical induction, the base case still is p of 1. Sometimes we need more base cases to work with, but the implication changes a little bit. So what we are looking at is if p of I is true for every integer I with 1 less than or equal to I less than or equal to k. So for every integer 1 to k, we know that p of I is true. Then p of k plus 1 is true for every positive integer k. If we can prove that implication, then what we can show is that p of n is true for every positive integer n. Now, the number of base cases that we need depends on how many steps backwards we need to use in our implication to prove it. So let's take a look at how this might build up. So let's consider a sequence A1, A2, A3, and so on of numbers. We can write this with the curly brackets and the A with a subscript. And we can talk about what the nth term in the sequence is. So I might have a sequence defined to be A sub n equals 1 over n. And I might have one that's defined as A sub n equals negative 1 to the n over n squared. I might have one that's defined as A sub n equals n cubed plus n. Those are all three different sequences. And each one of these is talking about n being a natural number. Another way that we can define a sequence is to define it recursively. So if we define a recursive sequence, what we do is we're given the first few terms. So say we're given the first k terms of the sequence. They're called the initial values. And then a sub k plus 1 is going to be expressed in terms of the values of a sub 1 up to a sub k. And more generally, whenever n is greater than k, a sub n is expressed in terms of a sub 1 up to a sub n minus 1. So whenever we have something like this, it's called a recurrence relation. So let's take a look at an example of this. I might be given a sequence and told that a sub 1 equals 1, a sub 2 equals 3, and a sub n equals 2 times a sub n minus 1 minus a sub n minus 2 for n greater than or equal to 3. This defines a sequence. So in this case, I've got two initial values, a sub 1 equals 1 and a sub 2 equals 3. I have the recurrence relation of a sub n equals 2 times a sub n minus 1 minus a sub n minus 2 for n greater than or equal to 3. And I can build the sequence up. So if I let n equal 3, then I'll have 2 times a sub 3 minus 1, or a sub 2, minus a sub 3 minus 2, or a sub 1. So I'll have a sub 3 equals 2 times a sub 2 minus a sub 1. And I know values for a sub 2 and a sub 1 that I can substitute in there. So I'll have 2 times 3 minus 1. And I get a sub 3 equals 5. So then I can bump up and I can say, well, what if n is 4? Well, a sub 4 equals 2 times a sub 3 minus a sub 2. And I have values for a sub 3 and a sub 2, so a sub 4 is actually equal to 2 times 5 minus 3. So a sub 4 equals 7. And building this up, I can keep on going and I can get to a sub 5 is 9, a sub 6 is 11, and so on. Well, you might notice that I have 1, 3, 5, 7, 9, 11 as my values in my sequence. I'm going through the odd numbers. And odd numbers we can get by 2 times a number plus or minus 1, or any odd number for that matter. So if I look at my n values in comparison to the odd numbers I end up with, I might notice, I might guess or conjecture that a sub n actually equals 2 times n minus 1 for every natural number n. So I have this guess, so let's prove it. So I have a sequence, it's defined recursively by a sub 1 equals 1, a sub 2 equals 3, and a sub n equals 2 times a sub n minus 1 minus a sub n minus 2 for n greater than or equal to 3. Then I want to show that a sub n equals 2n minus 1 for all n in the natural numbers. So to prove this, I'm going to use induction. I have the two base cases, a sub 1 and a sub 2, and I can check that those actually hold. So a sub 1, I have 2 times 1 minus 1 equals 1. A sub 1 was 1, and plugging 1 into 2n minus 1 gives me 1 also. So this holds for n equals 1. I also can check that it holds for a sub 2. I can plug in 2 for n, and I get 2 times 2 minus 1, or 3. I get a sub 2 equals 3. It's not necessary to check that one to have a proof by induction, but sometimes it can give you a little bit of peace of mind to check it. So then we're going to have our induction hypothesis. Now remember, with strong induction, our induction hypothesis is the thing that has changed. So we're going to assume that for some arbitrary positive integer k, that a sub I equals 2 times I minus 1 for all of the integers from 1 to k. So now we need to show that a sub k plus 1 equals 2 times the quantity k plus 1 minus 1. I can simplify 2 times k plus 1 minus 1 to be 2k plus 1. That gives me a better idea of what I'm looking for. So if k equals 1, we're going to again do this in cases. If k equals 1, then I have a sub k plus 1 equals a sub 2. And I have 2 times k plus 1 is 2 times 1 plus 1, which is 3. And I already know that a sub 2 is 3. So a sub k plus 1 equals 2 times k plus 1, when k equals 1. So now for my second case, I'm going to assume that k is greater than or equal to 2. And that's going to give me that k plus 1 is greater than or equal to 3. Now, I'm going to take a look at a sub k plus 1, and I'm going to use the recursive definition of my sequence. So remember, a sub n equals 2 times a sub n minus 1 minus a sub n minus 2. So if I have a sub k plus 1, it's going to equal 2 times a sub k minus a sub k minus 1. Well, by my induction hypothesis, a sub k equals 2 times k minus 1. And a sub k minus 1 equals 2 times k minus 3. So I can substitute those values in, and I get 2 times 2k minus 1 minus 2k minus 3. So doing a bit of algebra there, I get to 2k plus 1, and I get a sub k plus 1 equals 2 times k plus 1, which is my desired result. So by the principle of strong mathematical induction, I have that a sub n equals 2n minus 1 for all n in the natural numbers. Now there are some other examples here. They work the same way. You're going to prove a base case, and then you're going to have your strong mathematical induction hypothesis that you're going to use. And you're usually going to break it into 2 cases so that you can bump the value of k up to being greater than or equal to 2 or 3 or whatever, depending on how many terms your recursion equation goes back. And then you're going to go through and use the recursion definition, the recursive definition of the sequence to show the result that you want. Now, the reason that we bump the k value up, I don't think that we talked about this, is when we have these subscripts and we're subtracting, it's important that we are not getting down to having negative subscript values. So just keep that in mind as you go. And take a look at these examples, see if you can work through them, and bring any questions that you have.